Okay, so we are live on our first Code for Kids Hangout, and with our webinar. So we're going to have a webinar tonight about computational thinking. So welcome to everyone that's joining us. I hope that you're able to get on nice and easy with the links that were sent to your email addresses. So thanks for registering for tonight. So we've got many people from around the world joining us tonight. So we've got people from Russia, Switzerland, Canada, all around Australia, different places in Asia. So welcome to everyone. And I know that for some of you, your time zone might have been a bit of an issue, but it's great that you've been able to make it tonight. So just going to share with you just our welcoming page. So tonight we're talking about computational thinking. So I'm just going to share my screen. Okay, so we have our computational thinking webinar. So just if you are on Google+, if you can go and say that you are actually watching in the actual event page, that would be great, just so we can keep a count on how many people are around. And if you are using Twitter tonight, if you can use the hashtag Code for Kids to put out anything that you're finding interesting that you're learning. Just a little bit about me. My name's Kelly, Kelly Moore, and I currently working with Catholic Education Melbourne. And I am recently new to this position. I have been teaching for 10 years, and I have a really high interest in computer science and learning about how this can be used to enhance learning and also building my own capacity. So I love to learn new things. We welcome tonight Meredith Ebbs, who's our special presenter. And Meredith is an e-learning consultant, and she delivers and facilitates conferences and workshops. She's based in New South Wales, and she's also a consultant in digital citizenship and using technology to enhance 21st century pedagogy and social media. Meredith also speaks at many conferences around around Australia, and it has a particular interest in coding and using technology within education. Meredith is known because she has successfully developed and implemented Code Clubbers, and has also, which is a resource for secondary and primary schools, and she has also developed many computational thinking resources. So we're going to hand over to Meredith now, and she's going to present to us what her learning is. So if you would like to ask any questions, just going to start the question and answer app there on the side, so you'll be able to ask any questions on there that you would like to know. We'll be able to ask Meredith throughout the presentation. So thanks, Meredith.
Thank you, Kelly. So thank you everyone for joining us tonight. Like Kelly, it's very exciting to have lots of people from all around the world. So what I've done is I've made a presentation so you don't have to look at my lovely background. And so I'll just swap over to that for you. But what we'll be doing is we'll be talking about computational thinking. We'll be talking about why we should teach it, why we should teach code, and how that links into computational thinking, and how we're going to integrate that into the curriculum without adding more content, because that is the biggest problem that we have as teachers, is everyone wants us to teach more. So how can we get smarter about teaching that? So I'm just going to do a quick share screen. So hopefully that's all good for you. So computational thinking, what is it? It's using computers to help us solve problems. So we've got a generation of children coming through that could chew on phones and use phones before they could even speak. So now what we need to do is turn that into something that is powerful and get them to be creative with technology, so that when they become workers in the future, they've got understanding of technology, how it works, why it works that way, and then be creative about using it and implementing it in different careers. So before a problem can be solved, we have to understand the problem, and we have to understand what it is that's made that a problem in the first place. So computational thinking, according to Jeanette Wing and her two co-authors on her papers on computational thinking, is that it's a thought process that's involved in formulating the problem and solutions, so that when we have a solution, it is represented in a form that can be carried out by different forms of technology. So basically, we're trying to think like a computer. How can we think like a computer, and how can we solve problems so that a computer can pick up where we left off? So why do we need to teach it? We need to teach it for future careers. We've got a education industry which is set up initially to teach the masses how to read and how to write and how to do maths. But we're really good at doing that now. And now that careers have changed and they've formed, my job wasn't invented when I was at school. E-learning consultant. There's lots of positions that I've had over the years, and the only thing that was actually invented when I was at school was actually teacher. So we need to rethink what skills children will need when they graduate from school and from university. It's a new literacy, and digital literacy is starting to be thought of as a new way of learning. Along with reading, writing and maths, we need to consider digital skills as a literacy as well. These are the types of things we're going to be learning along the way. We're going to be learning about logic and problem solving, collaboration and communication and creativity. And you think about what happens in a workplace, those are the skills that we actually need when we're working with others. It's not how well we can sit an exam or a standardized test. So there's 4 parts to computational thinking, and they are decomposition, abstraction, algorithms, and pattern recognition. So decomposition is when we break down a complex problem into smaller and more manageable parts. And this is something that does actually happen in the classroom already without us realizing that it's happening. We do that in maths, we do it in literacy. So when we're presented with a mathematical worded problem, we need to find out what all the different parts are, what's the important information we need, and then we can actually break it down into something where we can solve the problem.
So it's great that, sorry, Meredith, it's great that you know, teachers would already be doing that in the classroom. So that's something that, you know, they're already doing computational thinking. It's just recognizing that they're doing it.
It's definitely that teachers are already doing it, and they'll be really pleased to hear that. And sometimes it's just about changing the wording in their program, or changing the wording in their language, in their everyday language in the classroom, so that we can start to incorporate this more technology-based language, so students will understand when they're, let's say someone wants to create an app. How do I go about making an app? And then communicating with the programmer on what I want it to do. And that's the language we want them to start to develop. Pattern recognition, every primary school teacher knows and understands pattern recognition. Every high school maths teacher would already be understanding pattern recognition with algebra. So it's about looking for similarities in problems that are outside of maths, something in science or something in language even. We're looking at pattern recognition. Abstraction is when we focus on the more important information only. When you're given a worded problem, particularly in maths, there's a lot of extra information that we actually don't need to solve the problem. So how can we work through problems and find out, well, we need this is important, but these bits we can leave out. And finally is the algorithm. and teachers will love to hear that this is actually procedure writing. The difference is this sort of algorithm isn't about making a cake and those standard steps that we'd have in a method. It's more detailed, and it's about writing a procedure that a robot could follow. So it's a really detailed procedure. An example would be if you would look up on YouTube how to make a jam sandwich. There's all these videos of teachers who are up the front of their classroom being robots, but then the children give instructions on how to get the bread out of the bag, how to spread the jam on the bread. And
we could put that up on our community, Meredith, as well. That's a really good one. I've seen that one. It's really good. That demonstrates that algorithms and that development of step-by-step really explicitly.
Yes, it does. And it's also, you can see in the graphic there, it's got decision charts, and you may or may not have seen these over on the right-hand side with the yellow boxes. These are decision and flow diagrams, and that is actually the procedure itself. So it's actually a really good way to introduce procedure writing, because it's so basic, and it even introduces loops. So you can see on the right-hand side there, when you get to the rhombus, it's got a grey arrow pointing back up. So there's the whole concept of encoding of a loop or a repeat, and you've got that illustrated in an algorithm when you're going through steps of a procedure. Do you have to repeat this step or not? Is there any questions, Kelly?
There's no questions at the moment, but if you're viewing, you can use the question answer app to ask questions to Meredith as she's going through.
Yeah.
So I'm sure they're coming.
I'm happy to answer any questions people have along the way. I can talk all night. So what does it allow us to do? It allows us to understand what a problem is, and it allows us, once you understand a problem, it allows you then to develop your possible solutions. So an example here is a Rubik's Cube, and Rubik's Cubes, personally, I cannot solve a Rubik's Cube, but I have met people who can, and it actually is a set of standard algorithms that, given the position of the colours on the sides, you just do a certain number of steps to solve it. So a Rubik's Cube is actually an example of how it's a massive problem that can actually be solved if you know the steps and developing the solution. So when we then present these solutions, we need to do it in a way that a human can understand, a computer can understand, and sometimes we need both to be able to understand. So it's about thinking of the problem. Okay, so now we're up to, well, how do I teach this in my classroom? And teaching it in the classroom, it's not about adding extra things to our curriculum or extra lessons. It's about getting clever and teaching what we actually want to teach already in the context of computational thinking. So, of course, the perfect example that everyone talks about is coding. And coding is we're not teaching our students to be a generation of programmers. We're teaching them to be problem solvers. So how do we do that? We integrate coding into maths. We integrate coding into English and procedure writing. We integrate it into creating games and all of those things that I've got listed there. So that is how it's not all, like, computational thinking is not, it's not coding itself. Coding is something that can help in computational thinking. So, it's good that teachers have a good understanding of that. Yeah, that's right. It's not about teaching the kids to be programmers. It's about the thought process that goes behind it. And I think the biggest problem for teachers is, once you've found a great tool, such as Scratch, for me personally, I found a great tool. There's a cat on the page. Well, what do I do now? How do I use that in my classroom? So it's about finding tools like Makey Makeys, or creating a game that allows students to identify prime numbers, or use this game to find the incorrectly spelt word. So integrating the use of the coding and making games to demonstrate their understanding of other key learning areas. So once you have written your game, so I'll just give you an example. I used Kodu, K-O-D-U. It's a Microsoft download, and I used that to teach narratives. So we talked about the narratives that happen inside games such as Zelda and Mario Brothers. We talked about how Mario has to find the princess, and he has to collect different items along the way. And once you've done that, you can write a storyboard, and then from that storyboard, you then build your own story. Then you go in and use your Kodu to make your own game based on your storyboard. For basic users, sometimes that's really difficult, and the game might be just, I'm going to collect apples and I'm going to score points, and at the end, I'm going to get a total. That might be the story. The goal is to collect 10 apples. But depending what year group you introduce it into, those concepts can become more complex. So incidentally, I did that storytelling unit with a year 4 group, which are about age 9 or 10. Is there any questions, Kelly?
No questions yet. I'm sure they're coming.
Okay. So as to offline examples, some people have difficulty getting internet and Wi-Fi and getting online tools to work. Some people have not very much access to technology itself. So for those schools and those teachers, I would recommend you use offline activities such as construction bricks, building patterns with construction bricks, maybe in the form of a binary message, or build something out of blocks and then hide it behind a book, and then give instructions to another friend who hasn't seen my construction how to build exactly the same as me, but they're not allowed to look at it. So those sorts of things would be achieving your English and your speaking and listening outcomes. And you also could then draw.
Teachers at the moment going, oh, I do that for my literacy activities all the time.
That's right. That's right. So, and you could then draw it, and then you talking about 2D shapes, and if they're getting older, you can start to introduce the 3D examples of constructions rather than just having a line of bricks that you might use in ages 5 to 7. You might have a sequence of beads or a sequence of bricks. Once they get into, years 3 to 6, or ages 8 to 12, you might actually start to incorporate 3-dimensional models, and they have to draw them and work out how to draw or design a net, or, those sorts of problems. And that then achieves maths outcomes as well.
Yeah, it teachers are nodding. I'm nodding.
Yes, there's lots. Everyone's doing. I think that's the biggest thing. The word computational thinking is actually a barrier in itself, because instantly I don't know what you're talking about goes on, and there's too much to do. We're just too busy, so that everyone thinks it's too hard, but actually everyone's doing it to an extent. It's just, like I said before, just a matter of modifying language, and it then brings in this whole new realm of technology or computational thinking.
Yeah.
So in the context of maths and literacy, you've got recounts and procedures everywhere. You can use it as a stimulus. You can do journals, blogs, wikis, how-to videos. You can do, I've used a tool called Pencil Code to teach space, position, angles, geometry. I've used it to teach number lines, positive and negative numbers. and you've also got your 2D shapes in there as well. So it's a very simple tool. It's a little bit like Turtle or Logo used to be, if anyone used computers in the 80s. And it's a really simple interface with a turtle, and the children need to use either, they can choose visual code or text. And I would say you could use that from late year 3 to year 10. You possibly could even use it into year 11 and 12, because you can make it as complicated or as simple as you want. There's also a lot of inbuilt workshops, inbuilt code modules which you can copy and paste and then modify, because sometimes before, on the previous slide, I mentioned hacking, and hacking isn't always a negative term. There's a lot of negative connotations around hacking, but sometimes it's about modifying something to make it better. And so we talk about the legalities of hacking, but then we also need to consider the learning experience of hacking. So if we can get a game that someone else has written that's open source, then we can modify that to suit ourselves, and that is a form of hacking. So for art and music teachers, they already do graphic design, pixel art and composition, but how do you to incorporate something that is code-based, then it brings in another element as well. And pencil code actually has a musical component to it where you can actually compose songs. Pixel art I've actually taught using spreadsheets, and you just minimize the rows down to the columns, so that they're forming small squares, and you can then design your pictures, and you can actually Google pictures and just copy to begin with, and then you can actually then move on to making your own.
I've used that before as well, the pixel art, and I found it really good with Minecraft characters.
Yes, great with Minecraft
characters with pixel art.
Yeah, and the thing is, I think then to tie that back to literacy, you could then get them to write procedures or recounts or reports, your research on their character, if they've done, say, Pokemons or, anime or manga type pictures, because that seems to be what a lot of my students have picked, is manga. Then they can do some research on those sorts of art forms, and I think it makes it a much more interesting classroom as well when you've got all these different things happening.
Yeah.
And I think science is also a really unexplored area of computational thinking. So an example for me was we were doing solar system, and I gave the students the distances from the sun to each planet in astronomical units and in kilometres. And just to put this in perspective, I didn't know what astronomical units was before I started the unit, so it was just something that sort of came up. We were trying to work out how we could plot the solar system on the back oval so that we could map it out and see exactly what distances were involved. And the back oval is 100 metres. And so what we did was I got the students to self-nominate. Do you want to do it on your own, or do you want to do it with me? And they were very good at choosing which group they should go into. And so half the class worked out their scales to themselves. They worked out if you multiplied astronomical units by 2.5, you would get about 100-metre scale. And that didn't include Pluto. They decided to drop Pluto off because it wasn't a real, as a dwarf planet. So they decided to drop Pluto off. So that was all the other planets from the sun. And it was great. We made up little posters, we put them above our heads, and then we flew the school drone over the top, and we played the video back in class, and you can really see how clustered together the first 4 planets are around the sun compared with how far the distance is to the other planets. And it really gave us a whole new perspective on how far the solar system, how far away everything is in the solar system, just even by looking at it laid out over 100 metres. But the computational thinking component was, here's a problem, now solve it. And it was a really positive lesson. And we had someone come down and watch us, you know, do the mapping. But I don't think it was as interesting to them because they hadn't actually gone through the whole process.
Sounds so interesting. And sounds like a great lesson to be a part of. I was just going to say to the viewers that are watching, if you're not sure where the question and answer app actually is, in the top corner, in your top right-hand corner on the screen, you'll see a little app launcher, which is your 3x3 grid. And if you click that, then you'll be able to access the question and answer app. So just if you're not sure where that is, that's where it is located.
So I think another way to integrate computational thinking is to start to investigate the design and build or design and make process as well, and incorporate your science, your technology, your engineering and your maths all into your classroom, and look at everything as holistically as you can. It's difficult in secondary because they have different faculties, but it is possible to work with other faculties if you can cross over units of work. I know our school has crossed over units of work on history of self and history of, you know, personal life timelines and self-esteem. So it is possible to do that. So it's, but STEM has got lots and lots of possibilities with computational thinking because you've got the problem solving and the building, and how am I going to make that work when people start to move into physical computing like Arduinos and Makey-Makeys, which can come in at a primary or elementary level as well. It's just about the teacher being open to different things and open to not always knowing the most. You know, the kids often know more than me, and I'm quite quick to admit that. And I think it's about a culture as well that we have to establish in a school as well.
Yeah. Okay, so we don't have any questions just yet. I'm wondering when Google Hangouts having its update whether people realise where the question and answer app actually is. But that's okay because we can still ask questions through our community, and we can ask questions, you know, through Twitter and things like that later on if we want to as well. So, but it has such potential in our classrooms, the computational thinking, and we are already doing it. We just need to recognise that we're doing it and start using that language, even with our students, and having our students identify that that's what they're doing as well. You know, that's creating real thinkers.
Yeah, on the Twitter feed, Will Cedorino said Minecraft in any activity is a winner, and I totally agree with that, Will. It's, you know, you can build 3D structures, you can do perimeter and area, it's all about construction, and you're meeting the kids where they are and the love of Minecraft. You don't have to know how to use Minecraft. No. There's some really good wikis. And if you read up on the wikis, you can sound like you're an expert, and the kids will respect you for that. So who else? Courtney said teaching narratives through coding. Yeah, she's just commented on the gaming one.
I think Will's also asked, can we have some examples of decomposition in literacy?
Oh. Well, I suppose breaking down poetry, you know, when you've got really complex poems and stories, and then breaking them down into bite-sized chunks, finding the rhyming, finding the grammatical structures and the syntax. I think particularly in high school with things, you know, when you start to get more complicated texts. But I think, you know, even in a picture book level, I suppose, if you've got kindergarten, you can be looking for, find all the words that sound like a sound, you know, trying to break down those words. We already do that. And so it's really just about finding that, using those words to describe what we're doing in our classrooms. But I would look at rhyming and structure even. If you've got a complicated book, you can, where's the introduction, where's the complication, where's the resolution in your narratives, or the same for a report, because that's the structure we teach. But can students identify that when they're given an example of written text?
Yeah. Okay, so thank you, Meredith, for all the information tonight about computational thinking. It is great to hear and confirm for teachers what they're already doing and how they can actually enhance what they're doing to make it, you know, to create that deep pedagogy in their classrooms for their students. Thank you to those people that reached out through Twitter, and for our next webinar, we will make sure that we have the question and answer app working properly. Before we go, I just wanted to show everybody that there is a Code for Kids website now where we're going to store our webinar. So this is the first one, and so it's called codeforkids101.com, and it just looks something like this at the moment, and it's the webinar's got a tab there, so we can have a look at our webinars there, but you can also ask questions through here as well. So, and if you haven't already joined our Code for Kids Google Plus community, please do so. Sorry, I didn't share the screen when I showed that, so I'll just share that quickly now, just to show you where that is. Okay, so there's the Code for Kids 101 webinar tab just there, so that's where our webinars will be stored. Also, I will be sending out to the email addresses that you registered with an evaluation feedback form. It's not very long. It won't take you less than a minute to fill out, just to get some feedback so we can plan for future webinars and see what you want to hear about, so that we can do more with coding and computer science, and expand our own knowledge and build our own capacity to be leaders in our schools on coding and computer science. So thank you for joining us, and we hope you enjoyed the webinar tonight. Thank you. Thanks, Meredith.
Thanks.